So let's take a look at another example problem here for ME 270 Structural Dynamics from Module 12. So in this example problem here, what we have is we have a three-story shear frame building that we can see off to the right over here. And they give us a lot of information about this building. They tell us that we have our F1, our F2, and our F3 given to us, where F1 is our 8 kips, F2 is at 10 kips, and F3 is at 18 kips. So we have our omega 1 at 10 radians per second, omega 2 at 20 radians per second, and omega 3 at 50 radians per second. And they tell us that our I is given to us as 750 inches squared, and we have our E over here as 29,000 KSI. Now, a lot of the other information is given to us in our initial diagram. So we can see here is down at the bottom, we have our distance across here is 18 feet. So from support to support, that's 18 feet wide there. From our height now, from our base here up to the first rigid girder is 18 feet. Our height from the first rigid girder to the second rigid girder here is 15 feet, and from the second to the third up here is 12 feet. Now for the supports along the way, this is given to us as 2i and 2i, and realize there's one on each side. And this here for the second set is 1.25i and 1.25i, and at the top here this is I and I. Now we also have the weight of these here, or our mass of these here, and notice that they give this to us in kip per feet. So this is our W DL is given to us as 0.75 kip per feet for our top mass, M3 there. Then for M2, our second mass, our middle mass here, our WDL is equal to 1 kip per foot. And here we have our WDL is equal to 1.25 kip per foot for our mass 1 here. So this is our X1, X2, and X3. So a lot of the information is given to us in the geometry and dimensions of this diagram here for our shear frame building. Now, what do they want us to find? They want us to find an expression for the steady state displacement response of this three-story shear frame building. So we're going to start with the beginning part of this problem here, and I'll show you in detail how we really go about looking and analyzing one of these and using this geometry and getting this problem set up and started. Again, a lot of the feedback I got was that people wanted a little bit more information, were having trouble and struggling getting problems started, knowing what key equations to use and how to incorporate the information given in the initial diagram and the initial wording of the problem statement. So I take a look at that, I've read through it, I've analyzed the diagram, I've read through the wording, what they've given me, what they're asking me to solve for, and I want to simplify that and create it all on one page to reference back to. So this I'm going to call my setup page here, and this is for our three-story shear frame building. I have all of my given information written out together in one neat, organized place with the correct units and the correct variable names for each of those. I've redrawn out my initial given diagram over here with my key information, easy to read and easy to reference back to. Have my given information here for my harmonic forces. My f of t is equal to f1 times the cosine of omega 1t, f2 is equal to cosine of omega 2t, and f3 is equal to cosine of omega 3t. And I come over here and I have now, they gave us my I value here of 750 inches to the fourth. My E value here is equal to 29,000 KSI. F1 is 8 kips, F2 is 10 kips, F3 is 18 kips. Omega 1 is given to us as 10 radians per second, omega 2 is 20 radians per second, and omega 3 is at 50 radians per second. Now, what are they asking us to solve for? I write this all right down here so I can reference back to it, an expression for the steady state displacement, and they tell us to use the superposition method. So again, primarily for my hand solution here, I'm just going to focus on getting this problem set up and started and where to go from there. You can reference back to the given lectures and a lot of the example problems in the book to see how to continue the problem solution to the end. So the first thing I want to do is establish what am I going to do to start the problem? What's my governing equation? What's my first step in the procedure for analysis? So I'm looking at here is I'm going to solve for my mass matrix here. But in order to solve for my mass matrix, I need to calculate the mass for each one of those M1, M2, and M3. So how do I do that? Well, I can say here, okay, I have my mass matrix here for each of those levels, 1, 2, and 3 for each of those girders there. And I know here for the first one, this is equal to 1.25 kip per feet, but it's 18 feet long. That's the width between the two columns. That's the width of that girder there. So 1.25 times my 18 feet gives me 22.5. But pay attention to your units. This is in kip. Then for the second level here, I have 1 times 18 feet is 18 kip. And for the third, I have 0.75 kip per feet times the length of 18 feet is equal to 13.5 kips. So now what I need to do, how do I get kips to mass? Well, kips is in a unit that we need to divide by gravity, and we also need to get it from feet to inches. So we take a look at this here. My gravity, my acceleration due to gravity here is 32.2 feet per second squared, but I want to be in inches per second squared here. So I look at this here and say, okay, well, for this here, my feet will cancel with my feet here, so I can multiply my 32.2 by my 12 over here in order to get that. So now I can take for 3, my 13.5 from right here, divide by my acceleration due to gravity in feet per second squared, multiply by the fact that there's 12 inches in a foot, and what I end up with over here for this, for my mass of that third girder there, is 0.035 in units of kips times second squared per inch. So really want to pay attention, note my units, and do unit analysis out through this whole problem, because it's units that we're not used to working with. A lot of times we're dealing with mass in kilograms, but now we're dealing with different units here, so we need to pay attention to how we do this and do our unit analysis to make sure everything works and that we do these correct conversions here to get the units to work out right. So do the same thing for mass 2. I can see, okay, here this is 18 kips, so 18 kips divided by 32.2 feet per second times 12 inches in a foot is equal to, my mass 2 is 0.0466 kips times second squared per inch. And then I do the same thing down here for mass 1, 22.5 kips divided by 32.2 acceleration due to gravity feet per second squared times 12 inches per feet is equal to, now here I have my 0.058 kips times second squared per inch. So now that I've taken that time to go through and actually calculate out each of my masses, for the mass of 3, the mass of 2, and the mass of 1. I rewrite that all over here now in a nice organized manner. Now I've color coordinated this to make it easy as we put this into our mass matrix to review everything goes. See, our mass 3 comes down here like this. Our mass 2 comes right here like this. There's my M2, and then my M1 goes right here like this. Now I have this lovely mass matrix here, a 3 by 3 matrix, where along the diagonal are my M1, M2, and M3, and I write down my units again because I really want to pay attention to that and make sure everything's correct as I do everything out through my solution to this problem. This is in kip times second square per inch. So what's the next step in our solution? The next step in the solution is our stiffness matrix. So we've already solved for our mass matrix, our M matrix, so now we want our stiffness matrix, or our K matrix here, and we can get this information in order to solve for this from our given diagram here, taking a look at the geometry and how these columns align and what's going on between them. And we can see, okay, for these top two, I'm going to use this relationship here that K is equal to 12 times my EI divided by L cubed, their length cubed. And down at the bottom here for this one here, I have this relationship here where it's fixed down at the ground down here of K is equal to 3 EI over my L cubed there. So now continuing on with our stiffness matrix here, again, we have our reference that I've copied back over here for how we come up with our relationships for K here. So now I take a look for each one of these for K1, K2, and K3, where given from our problem statement, we have our E value given to us as 29,000 KSI, and our I is given to us as 750 inches to the fourth. So again, pay attention to our units, make sure everything's correct, do out our unit analysis as we're doing this to make sure we get our K in the right values. So then we come down here, and what we see now is for K1, we have this relationship here. For K1, we have that K1 is equal to 3E times our 2I, because we're dealing down here with our 2I, relationship for K right there, all divided by L1 cubed, our length right there. So we can plug that information in, and we end up with 3 times my E value of 29,000 KSI times my I of 750 inches to the fourth times my 2 value from that 2I there, all times my L1. Now my L1 length, if I reference back to my setup page here, this is 18 feet right there for the length of that L1 from there to there. And this is times, now we want to get this in inches, so 12 inches in a foot. And then this entire thing is cubed. We do out that math there, and what we end up with then is that K1 is equal to 12.95. Now we do the same thing for K2, so our K2 equation right here is 12EI over L cubed. So I plug that in, 12EI, my I is given to me as 1.25 times our I value in the problem statement, divided by my L2 cubed. So I plug in my values there. This is 12 times my 29,000 KSI times 750 inches to the fourth times now my 1.25 right there times, or divided by, on the bottom here, 15, the length of this here, of this column there, times, again, 12 inches in a foot, this entire quantity squared, now that we're in inches, because our feet units cancel out there and there, those cancel. So that ends up being K2 is equal to 55.94, and for K3 we have 12 EI over my L3 cubed, again from this relationship there. So this we plug in here, my 12 is equal to 12 right there. My E is equal to 29,000 KSI. My I is 750 inches to the fourth times my I value here is just now 1 times I. We'll still put that 1 there just to correspond so everything is consistent throughout this here. All divided in the numerator here by my L3, which my L3 is my length from here to here, which is 12 feet times now my 12 inches in a foot. All this whole thing, quantity cubed right there. And when I do out the math of that, my K3 is equal to 87.41. So now that we have values for K1, K2, and K3, we can now create our stiffness matrix. So again, recall, for a 3-story shear building like we have in our problem here, we can reference back to a couple of the example problems I went through in the lecture slide and the textbook as well, and I have also uploaded a couple PDFs going through some example problems as well. And what we can see here is we have a general K matrix here for a 3x3 for our 3-story right here, where if our values here are K1 over 2 and K1 over 2, so this whole thing is K1, then, and this whole thing would be K2 because each side is K2 over 2, and this is K3 because it's K3 over 3. We end up with a matrix that looks like this, where our first element here is K1 plus K2, negative K2, 0, negative K2, K2 plus K3, negative K3, 0, negative K3, and K3 there. But for our problem here, we don't have a K over 2. We just have a K1, K2, and K3. So for our specific problem, what our general matrix is going to look like is like this here. So we're going to have now a 2 times K1 plus K2, a negative 2K2, a 0, a negative 2K2, 2 times K2 plus K3, negative K3, a 0, negative 2K3, and 2K3. So that's just a quick reference here to see why for our problem, because our K values are full, they're not K over 2s, this is what our matrix looks like. And we now have our values for K1, K2, and K3 that we can plug directly in there. So we can see anywhere there's a K1, we can start plugging in there for our K1 values. Anywhere there's a K2, we can start plugging in for our K2 values. Everywhere those are, and everywhere there's a K3, we plug in there for that value there. So that's exactly what we're going to do here in this slide there. Take those values, plug them in where they belong within this stiffness matrix, our K matrix here, plug in all those known values. So our K matrix now becomes, when we plug everything in here, 2 times my K1 plus K2, or my 12.95 plus 55.94, 2 times K2, negative 2 times K2 is where my K2 is 55.94, 0 is still 0, this is negative 2 times K2, or 55.94, 2 times, now this is a K2 and a K3, or 55.94 and 87.44, or sorry, 87.41 there. And then this is negative 2 times K3, which is 87.41. This is still a 0. This is negative 2 times my K3, or 87.41, and positive 2 times my K3, or 87.41 there. Do out my math, and this is my K matrix. Have up here 137.78, negative 111.88, 0, negative 111.88, 286.7, negative 174.82, 0, negative 174.82, and 174.82. So from here, now we can go back to our algebraic eigenvalue equation here, which says that K minus my omega squared M is equal to 0. Well, here's my K matrix there. This is my M matrix with my omega squared multiplied through. So I've just taken my M1, M2, and M3 and multiplied through by my omega squared. This is equal to 0 there. So now we can do our subtraction from matrix 1, a 3x3, minus this matrix here, which is a 3x3. And I have this relationship here that I can plug in. And now this, we need to take the determinant of it in order to solve for our omegas. So we need to solve for those omegas, omega 1, omega 2, and omega 3. So we can take the determinant. Now we could do this out by hand. You can see I started to separate out here, and I can go through and take the columns and rows and separate cover 1 and do all our matrix math. And you can see, I start doing things like this. It gets ugly quickly. So I recommend plugging this into your favorite numeric solver. MATLAB, there's even some programs online that you can use for 3x3, 4x4 matrix, things like that you can plug in. It gets a little tricky when you're plugging in terms of variables, but you could substitute this in. It's only one unknown variable here, or 3 unknown variables here, omega 1, omega 2, and omega 3. So you can solve those in, put them in as x1, x2, and x3 when you're doing those online solvers, or set this up in MATLAB. And I would suggest practicing setting it up in MATLAB. There's a lot of great examples. MathWorks has some that are pretty much plug and chug script files that you could substitute in and out for these matrix. So when you do that, what we end up with here is when we solve for our omegas, omega 1 is equal to 13.023 radians per second. Omega 2 is 55.41 radians per second. And omega 3 is 101.4 radians per second. So from here, now that we have our omega values from that determinant of that matrix, we can plug back into our eigenvalue equation here. We can see here eigenvalue equation is our k minus our omega r squared m times my mode shape that I'm looking for here is equal to 0. So I plug in my k matrix. I plug in now minus my omega squared matrix here. And now I have my m matrix there. I can plug in. My unknowns now are my omega 1, omega 2, and omega 3. So I need to solve for my omegas or my mode shapes. So when we do that, again, we've gone through this in another example problem as well. Again, you can do this by hand like we did before, or you could go through, plug this into MATLAB, and what you end up with, I'll leave you with the final solution here, so you could practice either doing it by hand or by MATLAB. We get our mode shapes here given by this matrix, and this is our modal matrix right there. And then our stiffness matrix, we can take K is equal to our modal matrix transpose times this right here times our modal matrix there. And when we do this out again, I would suggest plugging this into MATLAB. This will be a great way to double check to verify that you get these answers here when you do that. Now from there, if we wanted to solve for our modal forces from everything else they gave us in the problem statement, we could go through and do that. Like I said, my main goal with this example problem was to get you set up and to the point where you can just plug and chug through these or have a MATLAB script set up for those in order to get this. And we now have these omega 1, omega 2, and omega 3 values that we can plug in, which we can see now they gave us our omega term there, so we can back this out by simply plugging into this ratio here. So like I said, a lot of it from this point on to solve for our steady state solution they asked us to solve for is plug and chug based upon getting our mode shape and getting our omega values and getting that problem set up. So again, the feedback that I heard from a lot of students is a lot of people get stuck and don't know where to get the problem started, where to going. So that was the point of my example problems in this lecture for this module, was to get you set up and started in order to get to the point where you can solve, create your K matrix, create your M matrix, solve for your omegas, your frequencies, and your mode shapes.